Welcome to our MDK 6 webinar series, Modern Embedded Development Workflows. Today with session 2, Platform Components from RTOS and Middleware to Safety and Security. I also would like to welcome Trevor Martin from Hitex UK, and I'm happy to have him here once again today. My name is Wolfgang Fuller, and I will give you a short introduction about Hitex before the webinar starts. Hitex was established in 1976 as an embedded development company and has achieved rapid growth by developing and providing microcontroller development tools. With a global network, a branch in the UK, and many strategic partnerships, we ensure a presence wherever it is needed. Today, Hitex, as a proven expert, is also in great demand as a service provider for training and consulting, test services, development, and production services. Hitex supports all phases of your project, from the idea to the finished system. With over 70 employees, most of whom are developers and engineers, Hitex has excellent expertise and enjoys an outstanding reputation. Hitex is the preferred design house for all major microcontroller families from Infineon and an important distribution partner for ARM Keil tools and tools for hardware and software testing as well. The webinar today will be led by Trevor Martin. Trevor, our expert for ARM Cortex development, machine learning, and artificial intelligence. Trevor is not only expert, consultant, and trainer, but has also written a number of books and guides about microcontroller families and development software. Before Trevor takes over, I would like to ask you all your questions via the webinar tool. Trevor and the Hitex team will answer these after the webinar via email. And when the webinar ends or you leave the webinar, you can please take part in our short webinar survey. Thank you very much for this. And don't miss these dates. The last session in our short webinar series next Thursday at 11 a.m. German time as today. We will, of course, send you an invitation in good time, but you can also register right now because Anna provided a link to the registration in the chat. Yeah, Embedded World 2026, March 10 to 12 in Nuremberg, another opportunity for us to talk to you in person. Stop by the Hitex booth, and we look forward to seeing you there. And last but not least, not every company can say this, but we are celebrating our 15th anniversary. Join us and follow our journey on our website.
Hello, good morning, everybody. Thank you for joining us today. This is the second webinar in our overview of the MDK6 toolchain. In the previous session, I had a look at all of the core tools and the VS Code IDE. In this session, I'd like to have a talk about the available software components and platform tools that are included within the toolchain. So we're mostly here looking through the middleware in the section here, and also some of the additional supporting CMSIS packs. Alongside these, there's also a number of functional safety components that are included as standard within the MDK6 professional toolchain as well. And we will have a look at these towards the end. Over the lifetime of the Cortex-M microcontrollers or processors, ARM has developed a set of standards called the Common Microcontroller Software Interface Standards. These are a set of interlocking standards that attempt to make the use of C code on a Cortex-M based microcontroller very easy and transparent to do. So we had a look at some of these in the first webinar, and we'll have a look at some of the newer standards in the final one next week. This week, however, we're really going to focus on things like the CMSIS driver standard, which provides a common API to a range of peripherals that are on most microcontrollers, and also the CMSIS-RTOS API that standardizes the use of a small footprint operating system. And then to help to build more complex applications where we may have several different executables on the chip, or we want to control access and set up the memory protection unit, there's a very useful utility called CMSIS-Zone that allows us to set up partition and configure devices into more advanced modes. So first of all, we've really been supporting the use of a small footprint operating system on Cortex microcontrollers really since the chip was introduced. The device now has a lot of RAM, a lot of flash, and very high performance, so that it does allow us to use a small footprint RTOS. And ARM introduced a standard API called CMSIS-RTOS, which now has a range of supporting RTOS from different vendors. So within the Keil MDK6, there is RTX5, which is Keil's own operating system. This natively supports the CMSIS-RTOS API. But a number of manufacturers also provide CMSIS-RTOS compliant operating systems as well. Most significantly, there's a version of FreeRTOS that now also supports the CMSIS-RTOS API. However, if you're intending to use the Keil middleware, we'd recommend using RTX because the two are designed to work and are tested to operate together, so it doesn't introduce any unexpected problems. So the use of an RTOS really is very important in that it gives you a framework that helps you build more complex applications and also helps to scale things as well. So we have a central scheduler, and then we can run all of our application code as operating system threads, so they can be developed and integrated together, and then they can communicate via various different objects that are within the operating system, so semaphores, flags, message queues, etc. So this helps us build more structured code and also helps us reuse code in later designs as well. So again, it's a big step forward from over bare metal code. There's also on the Keil website, there's a tutorial with a link at the bottom there. So if you are new to an RTOS, it's possible to download those, and all of that tutorial is designed to run in simulation, so you can experiment with it on your own laptop. So it's quite a good learning course, learning route. Within MDK6, the RTOS is supported through the runtime environment manager. So here within the CMSIS branch, we can select the different operating systems that we want to use. So that could be RTX, it could be FreeRTOS. More recently, there's also been support for Zephyr introduced as well. We'll talk about that later on. And also we need to have a tick source, so we can select the SysTick timer, which is generally used as the standard timer on the chip. Once we've added the operating system, its configuration is done through a configuration wizard within a config header. So again, here we can set up the memory resources and number of threads and different features that we want to use within the device. So then once we compile and build, we can run the code within a debugger. And there's also a very useful plugin that we can install via the extensions within VS Code. And this gives us a up-to-date view of how all of the threads are running on the chip. So here we can see the chip that's running, the status of all the other threads, and also very importantly, how much memory that they're using. So again, we have a very deterministic use of the memory usage. We can monitor it, and we can also, if we enable that feature, we can see the maximum amount of memory that it was used. So in many ways, we can also look at, we can also look at the timing and execution of all of the threads, so we can get a very clear idea of how the code is executing on the device. And certainly within the MDK5 debugger that you can still use, there are a lot of tools in there that allow you to measure how the threads are running, how they interact together, and we can get a very clear idea if the code is meeting real-time deadlines that are within our application. And this can be a lot clearer than simple bare metal code as well. So a lot of advantages to using an RTOS. Namely as well, we can use an RTOS to impose a good software architecture. So this can be designed as a set of software layers, and this is also then incorporated into the build system that we saw last week, that we can define a hardware layer, which is all of our drivers. So typically here we can use the CMSIS drivers board support package, and that can be defined as a software layer and added to our project. The bulk of our code can then be designed as software components, and in addition we can define additional layers for those to include other features or parts that we need to build them. And then at the top we can write our application code, the sort of the business logic if you like, as operating system threads that then talk to the components, and the components then talk to the hardware layer. So this gives us a very structured layout for our code. It also means that all of our software components are isolated from specific hardware and then can be reused on later projects. So this gives us a much more sophisticated build system, code reuse, and more advanced debugging as well. So also provided with within the MDK Essentials and Pro is the Keil middleware. Now this has been developed over quite a number of years, and it was included in the previous Plus and Pro versions of the MDK 5, but now has effectively been open source and included in both the Community Edition, Essentials and Pro Edition. So within here we have some of the key components that allow us to use the more sophisticated peripherals that are on these small Cortex devices. So the middleware provides a file system. So this can work with SD card, external flash, RAM or SPI memory. It also provides a network component. So this gives us a full TCP/IP stack and application layer. And finally, we have a USB component that supports both USB host and device with standard class types. And all of these interface to the hardware via CMSIS-RTOS. So we need to have the operating system running in order to use the middleware. And also we need a set of CMSIS drivers that allow us to talk to the hardware. So the middleware plugs directly onto the CMSIS drivers and CMSIS-RTOS. For security, particularly in terms of the network component, there's also a stack called mbed TLS that provides us a full TLS library that's quite easy to integrate and is also written specifically for small microcontrollers. Additionally, we have debug tools, so CMSIS View, which provides the event recorder. So this shows us all of the annotations that have been set within the middleware components. So as we're running the system, we can get a very good view of how the component is actually executing on the device. Now, with the introduction of MDK 6, when you're using the middleware, you should ensure that you're using version 8 or later of the middleware pack. If you're using MDK 5, we'd recommend that you stick with version 7. So that will work better with MDK 5. I think if you start using version 8, that's more optimized for VS Code, etc. So you're likely to have some small problems. So as we discussed, we need a range of CMSIS drivers to work with the middleware stacks. Generally, these should be provided by the silicon vendor and written specifically for their devices. So you shouldn't really need to develop any of the CMSIS drivers. They should be ready done for you, and a few clicks should then allow you to set up your middleware stack. So it's quite important when you're selecting a device to check the pack support and ensure that there's an appropriate range of drivers available, so you don't select a wrong device and then can't use the middleware easily. Within the software packs, as well as the CMSIS drivers, there is a driver validation framework. So when we install the driver validation pack, when we start a new project, this will appear as a template that we can select when we define a project. So this gives us a testing framework that allows us to select various CMSIS drivers and then run a range of confidence tests over them to check that the driver's correct, and also to an extent that the hardware is correct as well. So we can do a range of loopback tests. There are also a set of servers that can run on a board, so a SPI server or a UART server, so that we can talk to a second device to check that the driver is fully functional. So this gives you a big confidence when we're getting started, and also serves as a board bring up mechanism as well. So it's quite a useful one to experiment with. Once we've selected the particular driver that we want to use, again, within a header file, there's a configuration wizard where we can set up the parameters, the communication parameters for a particular peripheral, and then the range of tests that we want to execute. So instead of having to write lots of code to test our hardware board, we can simply add this project, select the particular tests and loopback tests, etc., that we want, and then we can execute those tests and get a test report that proves that both the driver and the board are working correctly. So in terms of the components, there is a USB component, so this supports both host and device. It also provides support for a range of standard classes within the USB standard. So mass storage class will link up to the embedded file system. The human interface device gives us support for buttons, LEDs and screen, etc. We have a communication device where we can do virtual COM port, and it's also possible to write a custom driver as well. Within the USB device, there's also audio class, so we can have a microphone and speaker connected to the board. And again, ideally, as I say, we'll have both the host and device CMSIS drivers written, so we don't have to do a lot of low-level work, and we can just concentrate on building our application. In terms of the network, so this is the most widely used popular component. This provides a full TCP/IP stack, both for Ethernet, Wi-Fi and modem use, so it'll integrate with most communication devices that you're likely to need. It will also easily integrate with mbed TLS to provide a secure connection. And then on the device, we either need an Ethernet driver, UART for a modem, or we can use the Wi-Fi driver that again will talk to common modules through SPI or a UART. In addition to being a TCP/IP stack, the network component provides a range of services as well. So these things like web server, FTP, TFTP, etc. So you can build a full network application quite easily and quickly. There are also a set of supporting utilities and templates that provide the critical code for this. So again, you can bring up a full TCP/IP stack web server very, very quickly. The file system, again, is a very useful component in that it will give us a fat file system on any drive that can be removed from the microcontroller. If it's a fully embedded volume such as flash or RAM, then it uses a custom file system. So there's and the file system will automatically choose which one it's going to use. So in terms of drives, we have USB, multimedia card. We can use internal, external RAM, and also flash memory as well. And again, these will match up with the CMSIS drivers that ideally are provided as well. Now, when we add a networking, or when we select a networking template, when we begin our project, we will be asked to select a software layer. So when we have selected a particular evaluation board, that will come with a number of layer definitions within the pack. So here we can select one for an IoT board. There may be a range of board support, layers that have different peripheral configurations. And when we select those different layers, within the layer description, it announces what peripherals are supported within that particular layer. And then within the middleware template layer, that announces what peripherals that it particularly needs. So there is a resolution done between what the project requires and what the layer provides. Again, once all of that is satisfied, we can then go ahead and start building our project. So this kind of links together a bit like Lego bricks, and there's a degree of checking as well as the project layers build up, that all of the dependencies and requirements are resolved inside. So once we've then added our middleware reference application, it will typically then include a range of starter projects, so we can select any one of these projects and build it and then test it down on our hardware. So again, there's a standard set of projects that have been added for the networking component that allow us to test most of the features and build on those as we build up our project. And these provide very, very good starting points. We also have a range of tutorial examples as well. These have been done for MDK5, but will be ported over into MDK6 and released as packs as well, like we have done for the RTOS tutorial. So once we've added the component, any further configuration is done through config wizards that are within the header files. And the layout here is fairly consistent. Once you're a little bit familiar with it, you can then just work through the stack, set up the Ethernet configuration, the TCP UDP configuration, and then the application layer configuration as well. And then that allows you to go and then concentrate on building your full application. Some of the newer CMSIS drivers, so the CMSIS Wi-Fi driver is a standardized driver that sits on top of either the CMSIS USART or CMSIS SPI driver, depending which Wi-Fi module that you're using. So again, this fairly easy to integrate stack, so that when we're using this, it's just a matter of selecting things within the RTE and then going through the configuration wizards to set them up, connect to a test server, and then we can validate that it's working correctly. So again, as we saw at the beginning, the driver validation software will allow us to test out the Wi-Fi module quite extensively. And there are a range of these are supported. So again, if you are going to use one, you need to check that it's a supported module. So there is a list, and also you can see it in the drop down within the RTE. Many of these are available as Arduino boards or micro click boards, which go into standard sockets on evaluation boards. So building up the hardware and testing it is again quite a rapid process. So typically what we're doing, particularly when we're talking with an IoT device, is that we want a TCP network, and then we want to have TLS inside that. And then typically we're using MQTT to transport data, message queue telemetry transport. And that data can be represented within JavaScript object notation or concise binary object notation. So JSON or CBOR. Now we have again support packs for both the TLS, MQTT, and also JSON and CBOR. So within the RTE, once the packs are installed, it's a matter of selecting all the elements that you want in the stack, those get added to your project. Again, we have configuration wizards to set those up and templates so that we can test those out quickly. And those will run on the real device hardware using the network component or the Wi-Fi component. But also, second from bottom, there's a virtual socket. So this is designed to work with the ARM virtual hardware. So it's possible to build up a simple IoT node that has file access to your underlying PC, and also has a socket that can talk to a remote cloud server. So you almost have a small IoT node that you can develop with in simulation before moving on to the hardware. And again, this is quite an interesting way to work, particularly if you haven't quite decided on a device yet, or you don't have the evaluation board or even your own hardware. Again, provided as a standard stack is mbed TLS. This is a very modular security library that provides full transport layer security, but it includes modules for hashing, cryptography, public key cryptography. So any one of those components can be used in isolation. So particularly the hashing is often used for verifying images that are going to run on the target, etc. So this is a free open source stack, and it's free to use for commercial and non-commercial use. And again, there is a full tutorial available for this as well. Again, if you want any of these, just raise a message and I can sort those out for you. Now, in addition to communication security, there's also, under the Cyber Resilience Act, we need to ensure device security as well. So over, again, I think the last 5, 6, 7 years, ARM have been running a project called Platform Security Architecture. So this provides a set of standards, utilities, and also firmware that helps ensure all the critical aspects of your device security. There's also a PSA certified certification as well that can be used to prove that you've met the CRA. And also the CSIP standard as well can be used to say that you've done enough testing to meet the Cyber Resilience Act. And very often these are self-certified, which are then validated by a security lab. So it's a fairly painless route to meet this CRA, provided you've done the underlying work. So one of the key aspects that the platform security architecture defines is that we have to partition our security software. So we split this into a non-secure region, which is the, pardon me, the bulk of our application. And then all of our secrets and secure services are placed in a separate executable partition. And then we only have a partition manager, which provides a gateway to communicate between the two. So we just have one messaging path that allows us to access the secure secrets and crypto services that are provided by the secure code. And in order to manage this, there is a utility called the CMSIS zone utility. So this allows us to define the secure regions, non-secure regions, and then we can allocate different regions of code into either of those regions. So this then generates the linker file, the code for the memory protection units, the security attribution unit that are on the ARMv8 hardware. So this allows us to graphically sort out our code between the secure and non-secure software and not make any silly mistakes when we're trying to manage several different build files. So in terms of implementing this security architecture, it can be done on an ARMv7 architecture chip. So typically you'd use the memory protection unit to enforce isolation between the secure and non-secure regions. And if you have an appropriate microcontroller, It may have some additional peripherals on there, some crypto accelerators, true random number generator. But vitally, the main thing that it would need is to have a secure boot process to ensure that the code starts up and your firmware is running and hasn't been interfered with. However, to make an easier path and probably a more expensive chip, you use one of the newer ARM v8 based microcontrollers, so Cortex M33, 55 and more recently M85. And this has the trust zone security peripheral that enforces hardware partitioning, and also typically will then have a range of security assistive architecture on the chip as well. So this does make life a lot easier to develop a truly secure device. In addition to network security, we also have to consider device hardware security. Again, there are now a range of attacks from power analysis, glitching, electromagnetic fault injection. So these are beginning to present a real issue with people trying to extract secrets and information from your devices. So there is a range of equipment from a Canadian company called New AE Technology. So this provides test equipment to try and validate your hardware and make it immune from hardware attacks. So the graph on the right there is basically a power analysis, and this is looking at the paths, the energy usage through the paths taken by a simple password function. So most of the attempts at putting in letters of the alphabet will fail, but when we put a correct value in, the code takes a different path, which leads to the blue graph that is then easy to isolate. So by injecting a character at a time, we can analyze how the code reacts, and then we can deduce the password a letter at a time. And again, there are other attacks on the AES standard to extract its key. The same equipment can also break the RSA cryptography as well. So there are real threats here, and you need to consider if you need to take these into account with your particular application. In addition to security, we also have safety. So there's now a range of industries where we have to produce our equipment to a safety standard. And this then does give us a big overhead in developing our project. So again, we have to define our safety cases. We have to have functional safety compiler. We have to have a functionally any external components have also to be certified as well. So this is quite a big overhead when we come to develop both a safety and also a security application as well. So within the MDK6, ARM now provides a range of pre-qualified components that we can use to provide a platform for our safety application. So at the moment, all of the components and tools that we've discussed are available in the MDK Essentials. So again, for 80–90% of projects, that is the tool chain that you would need. If you're doing a functional safety application, then the MDK Pro provides the Keil runtime safety system and also a safety certified compiler. So this gives you a fully certified platform that you can start developing with, and there are no further licensing or runtime costs. So this gives you an incredibly easy and cost-effective entry route to developing a safety system. In addition to the safety components, the Pro also provides a range of legacy components. So particularly the ARM compiler 5, so a lot of people are still using this. So the Pro will give you an additional license to use AC5, and also the older legacy tools, so the PK51 for 8051, and also the 166 compiler as well. So if you want to also try out the MDK6, there is a community edition, and this provides a license that gives you, I think, most of the features that are in the essentials. So you have an unlimited code use, and you can also try out all the middleware as well. So the functional runtime safety system that's in the Pro includes a set of pre-certified components. So the major one here is the Hitex-RTOS. So this is a fully certified safety compiler that you can use with the MDK Pro license. Also the debug agent, the event recorder. So this is used to send annotations in your code up to the debugger. So there is a certified version of this as well. So that can provide you with on-chip visibility as the code's executing. And then also CMSIS core. So these are the functions that are typically talking to the Cortex registers. There's a certified version of that as well. In addition, there is a certified ANSI library that runs with the functional safety compiler. So again, this provides you a very complete code generation system as well. And importantly, the functional safety compiler is also certified for all its different optimization levels. So this means that you can still get highly optimal code. Some other compilers that are safety certified are only certified for a minimum optimization level. So again, this is an important thing to check. A number of silicon vendors have also introduced software test libraries. So this will do RAM and CPU checks, both at startup, but we can integrate that into an RTOS thread, so we can run safety test code as the application is running as well. So these are available at cost from ARM. But again, as I say, a number of silicon providers have licensed them so that they're free to use with their devices. Now, another important feature of the functional safety RTOS is that it can do process isolation. So this separates the safety critical code from any non-critical code that we want to run on the chip as well. So essentially here, we're programming the memory protection unit so that we isolate the two different types of code. So this means that we then only need to certify the critical code, and we don't need to certify the full application that's running on the chip. So this greatly reduces the overhead of work that we have to do. So this works effectively by setting up the memory protection unit so that every time we do a context switch, we reprogram the memory protection unit and to allocate resources to the thread that's running. So we're kind of opening a window and allowing it to access its area of RAM that it's been allocated, and also the peripherals that it's been allocated as well. So every time we swap to another thread, the MPU is reprogrammed and resources are then granted to the executable thread. In addition, each of the threads can be granted a safety class so that they can only talk to a thread of the same class or lower. So a thread with a lower priority class can't talk to a higher priority thread as well. So again, we can enforce communication, and we can also grant a shared region of memory as well for devices to communicate to each other. Interrupts are managed outside of the MPU system, so they're still fully deterministic and will respond to those without absolutely any overhead or latency. Again, this gives us another configuration issue. We have to lay out all of our threads manually. So we have to do static allocation of the thread memory. So this is kind of doing the linker's job for it in a way. But here, again, we can use the CMSIS zone utility so that we can define the resources that are on the chip, each of the threads that are running, and then we can allocate the RAM and peripherals to a given thread. That will then generate the linker script files, the MPU table, which we can then add to our project. So this, and again, CMSIS zone is a free-to-use utility that just can be downloaded off of GitHub. In addition to the process isolation, there's also temporal isolation. So here we can have thread watchdogs that can be programmed to ensure that a thread runs at within a certain window and also doesn't take too much runtime. So again, if the watchdog times out, it will raise an alert, and then we go into the fault handler. And again, there is a more advanced fault handler that's provided so that we can go into a sort of a safety running mode as well. So that's giving you sort of an idea of the components, etc., that are available within MDK6. In the final webinar in this series next Wednesday, we'll start to have a look at the more advanced use of LLMs within VS Code. So we're looking at how we can use Copilot and also agent workflows. And then we'll also have a look at the machine learning enablement that's available to run inside MDK6 as well. So this is gathering data and building real world machine learning and DSP applications. We also look at the hardware, so we can see the hardware support that's been added to new devices. So Helium and also the Ethos NPU as well.